In that case, it's my great pleasure to welcome Neil Hoffman for our seminar today.
Thanks. And thanks for the opportunity to speak here today. I know obviously this semester is different for everybody, but it's giving this talk is something I've been looking forward to, and so feel free to interrupt. Feel free to interrupt and ask questions. My goal for the talk is to really state a number of conjectures related to this one problem of not complement commensurability, which I'll define a little bit later. And these conjectures fall into two kind of flavors. So the first part of the talk, the actual conjectures, are probably going to be, they're kind of highlighting problems that are also of interest to people outside of this narrow subject area. And then the second half of the talk, the conjectures will be maybe more focused on this exact set of problems. So the first part is really seeing how it interacts with other fields and questions, and the second part is to really focus on some of these conjectures that are more specifically related to commensurability. Okay, so I wanted to obviously start out by defining what commensurable manifolds and orbifolds are. So for the talk, I'm really going to focus mainly on hyperbolic objects, hyperbolic orientable objects. And so a hyperbolic 3 orbifold can be thought of as a hyperbolic 3 manifold, where maybe a group of symmetries is acting on it in a manner that actually fixes points on the interior, right? So if you're unfamiliar with orbifolds, you can get away right now with kind of thinking about these manifolds, or really the way I want to think about these objects is as quotients of H3 by some group of isometries. And I just don't, I'm not going to be worried about these groups, say gamma 1 and gamma 2 here, being torsion free, right? So we've got two quotients of hyperbolic space, and they're commensurable if they share a common finite sheeted cover. So we've got Q1 and Q2, and there's some common cover Q naught. And the only thing we care about here is that Q naught is finite index, a finite degree cover of both manifolds. So M and N in this little diagram, they just have to be finite. Now there's also a statement about commensurable groups that you can make here. So if we started by fixing gamma 1, then I can draw kind of the same picture, and I would have gamma 1 and gamma 2. This is a slight lie because I would have to choose the right conjugate of gamma 2. And then what we would see is that we would see a common finite index subgroup of both of these things. And when you look at the group picture, it then becomes clear that commensurability forms an equivalence relation on the set of hyperbolic 3 orbifolds. So that can be really useful and allow us to exploit lots of different properties. So it kind of organizes the set of hyperbolic 3 orbifolds, and it organizes them into commensurability classes. These classes have kind of nice properties in that the geometric data associated to any element in the class is roughly the same. So like if you that's of course very loose, but if you took like the volume of one of these objects, then actually if you take the volume of two objects in the same commensurability class, those two volumes have to be related by a rational number because of how commensurability is defined. And then more than that, like any kind of geometric data that respects covering is going to be rationally related. So something like the length spectrum of the manifold. And coming from Westwood. Okay. In the kitchen. Okay. Can you? Sorry, I've got kids in the background. Right. So there's also, when we look at the group data, right?
Actually dumped water on the floor.
Okay. Can you get a towel and clean it up, Charlie? Sorry. It's a little bit of a high wire act, but right. So and I think my kids have just revealed the man behind the curtain here. So that's we'll see what happens. Right. So commensurable manifolds and orbifolds really, if we look at the group picture, we can associate arithmetic data to the representations of the groups, and a lot of that data is going to be the same, right? So we can kind of work over the same fields in order to define the entries of the elements, right? So and then if we want to look more globally at the classes of hyperbolic three manifolds and orbifolds, in fact, I'll stick to cusp hyperbolic three manifolds and orbifolds. We actually have this nice dichotomy for commensurability classes, that either commensurability classes have a particularly nice element, H3 mod PSL2 OD.
Puddle on the floor so it can jump in.
Okay. Hold on excuse me for a second. I'm going to be right back. Everything's fine. Just a little bit. The floor is a little bit wet now, but anyway, everything's fine. Right. So to abruptly switch back, so commensurability classes either have a really nice object in them, H3 mod PSL2 OD, where OD is the ring of integers in a quadratic imaginary field. So like a great example of this is the figure 8 knot complement. Basically, you can compute the hyperbolic structure by hand because you're working over a really small field. So you can like solve the equations you need to solve and write everything out. And also these groups just naturally are discrete because because OD is discrete in C, right? So like these are really pretty objects. And if you don't see one of those things, then what happens is that the commensurability class will have a minimal element in it. So that's really kind of a nice trade-off, that either you have this really pretty object in your commensurability class, or you have a minimal volume element. And in fact, everything in the commensurability class will have to cover a certain minimal volume element. Okay, so the main question for this talk is really, how can we find two hyperbolic knot complements in the same commensurability class? And so what are the various constructions, and what open questions are related to those constructions? So, before we had two orbifolds that shared a common cover, and now we want two knot complements to share a common cover. The first thing is that the figure 8 knot complement is the only knot complement in its commensurability class, and this is a theorem due to Neumann and Reid. And he actually showed something stronger than that, and that is that the figure 8 knot complement is the only knot complement commensurable with one of these nice quotients, these PSL2 OD quotients. So what that means is that as long as we just throw out that one thing, anytime we see commensurable knot complements, there's going to be a minimal element in the commensurability class. And so instead of having to worry about a finite cover, we can actually look at a finite quotient. The advantage to this is that you're searching one object for covers, and kind of the degree of these covers is more naturally bounded, or you can start to really probe an object that you can get your hands on and look for knot complements covering that object, right? So, there's the conjecture is that in fact knot complements in a commensurability class should be very rare. So it's normally stated, right, that it's the commensurability classes of hyperbolic 3 manifolds contain at most 3 knot complements. I've just kind of teased out the conjecture to say 0, 1, 2, or 3, because over the course of the talk, we'll see examples where each one of those numbers are hit exactly, or I'll describe how we can hit each one of those numbers exactly.
So Neil, I always thought of that as the Reid-Walsh conjecture.
Oh, wait. Oh yeah, sorry. Yeah. Thank you. Yeah, so sorry, you're right. Thank you, Steve. Right, so first, I guess if you take PSL2 OD and you take any D that's not 3, then you're going to see 0 knot complements in the commensurability class. So that's like an infinite set of examples where we see 0, and then Reid and Walsh in the paper that has this conjecture in it, they show that 2-bridge knot complements are the only knot complements in their commensurability class. So there's in fact infinitely many knot commensurability classes with exactly 1 knot complement in them. Right, and so the other thing is that if the conjecture is true, then looking for knot complements is one way to kind of identify and get your hands on an object in the commensurability class, and everything should be rationally related to a knot complement, right? So that's further motivation for why we might care about these things. Okay. When we have a knot complement covering some orbifold, right, say the minimal volume orbifold in the commensurability class, or just any other intermediate quotient, we could ask how this quotient operation is going to happen, like what properties we can say about it, and really the thing that we might want to know about is this regular or irregular? Namely, when we look at the induced inclusion map on the fundamental groups of S3 minus K and Q, is the knot group sitting as a normal subgroup of the orbifold fundamental group of Q, or is it not a normal subgroup? And in fact, there's a topological criterion for looking at this question and answering it, and it just depends on the cusp type of Q, right? So we've got a knot complement, and that's going to have a torus cusp, and then Q is going to be some quotient of that knot complement. So the cusp of Q is going to be some quotient of a torus, and we're assuming that Q is orientable, so that the cusp has to be orientable. And there are only 5 quotients of the torus that we can see. So that's going to be a torus itself, or what we can do is take a torus and kind of rotate it by an angle of pi. And when we do that, we're going to get a sphere with 4 cone points of order 2 as a quotient. And this quotient operation preserves the meridian and preserves any basis, right, for up to inverses. So it really allows us to get a regular quotient, and that's what Neumann and Reid observed here. That if we look at a quotient from S3 minus K to Q, and Q has a torus or a sphere with 4 cone points of order 2 as its cusp, then that quotient is going to be a regular quotient. And if the cusp is anything else, if it's one of these 3 objects, the cover is irregular. And you can just see that by looking at the homology of the knot complement, that the homology can't be preserved by a rotation of order 3 or order 4 acting on the cusp, which necessarily would show up in the peripheral subgroup of Q. In the case, the cusp is one of these special orbifolds, these spheres with 3 cone points. We say, S3 minus K, so the knot complement covering this, has hidden symmetries. So because the cover is irregular, there's going to be some regular cover of Q that has more symmetries than S3 minus K. And so, you have to go to a cover to kind of see the maximal symmetries, like the maximal set of symmetries in the commensurability class, or, you have to go to a cover in order to see something that will quotient down to the minimal volume orbifold in the commensurability class by symmetry, right? So they're hidden from us is the motivation for this terminology. And so from now on, I'll kind of break the question up into these 2 parts. Like when, based on this quotient, like we'll look at what's happening in the case of a regular cover, and we'll look at what's happening in the case of an irregular cover here. So the previous slide had S3 minus K covering one of 2 types of cusps, and by work of Steve and co-authors, Balo, Sabanu, and I guess Sabanu was at UCAM, right? He got his PhD there, yeah. And then Walsh, and I guess when you were working on this project, Genevieve was also in Montreal, right? So, yeah. So, but
it started when Radu was a student and Genevieve was a postdoc.
Okay. Yeah. What you guys did was looked at kind of quotients, and in fact, if this Q here has a sphere with 4 cone points of order 2 as its cusp, so if you have 2 orbifolds that are covering, 2 knot complements covering the same orbifold, and it's regular, this would have one of 2 cusp types, but in fact you can kind of we can now see that there's an intermediate cover that has to have a torus cusp. It could be trivial, but we can always kind of just see these covers as covers down to a torus, which means that in this case these covers are naturally cyclic. Right, so we're just quotienting by a cyclic group of isometries in order to get down to this object with a torus cusp. And so you can go further, and in fact, that's in fact, what we can say is that each time we see a cover by a knot complement, or Boileau, Boyer, Sabano, and Walsh kind of went through and worked out all the details to say that each time you see a cover of QT by a knot complement, you're gonna see a cover corresponding to a cyclic filling of QT, right? So QT has to have some, we have to be able to fill a peripheral curve of this torus and get an orbifold with finite cyclic fundamental group. And then more than that, if we assume that QT is an orbifold with non-trivial torsion, and we have two knot complements covering it, then those QT are completely classified. So they fit into this family of knot complements in the solid torus that have a second solid torus filling. So a cosmetic surgery on the solid torus, and so they're called the Berge-Gabai knot. So you would just take a Berge-Gabai knot and attach a torus with some torsion along the core, and that's how you build these QT, as long as you pay attention to the linking number. So the point is that it's only the manifold side of the problem that's open anymore because of the work that's done here. So for the next couple slides, we'll be really focusing on QT, where QT is a manifold. Okay, so right, so if we do have S3 minus K covering this QT, then like I said, what we can do is we can fill to some orbifold O, where this is homeomorphic to S3 minus K mod a cyclic group. And then you can pull that up to the universal cover, right? And we can kind of see, how this diagram basically commutes, right? So each kind of the idea is that each cyclic filling allows us to build a different diagram like this. And so really focusing on how these cyclic fillings of QT can arise is going to allow us to understand how to build commensurable knot complements in this via this construction. Okay, so and so the first thing that we could do is just assume that we have a knot complement for QT, so that this thing that's covered by multiple knot complements, actually part of the diagram collapses, and we have a knot complement that's covered by another knot complement. And so really what there are lots of knots known to fit into this picture. There are what are called Berge knots conjecturally. And what we can say is that this S3 knot complement is actually some LPQ minus K prime, right? So this is homeomorphic to some other knot complement in a lens space LPQ, where P is the degree of the cover from S3 minus K1 to S3 minus K2. So we have some cyclic cover. The degree of that cover is actually the size of the order of the fundamental group of the lens space that we obtain by filling. And what the Berge conjecture says is that this K prime is a 1-1 knot, can be realized as a 1-1 knot in the lens space LPQ. So what it's saying is that you take a Heegard splitting for LPQ, and then we would put the knot mostly on the Heegard surface, but we might need to have at most one bridge, right? And in fact, if we want things to be hyperbolic, we'll need exactly one bridge to realize this LPQ minus K prime. Right. So so then we could ask, okay, well, is this the general picture? Is this like what we would do to find even when we explode things along the left-hand side to build, if we have two knot complements covering that QT, where each cover is non-trivial. And in fact, the answer here is no, that the Berge conjecture doesn't quite carry through exactly. So instead, what we'd have is we would have this QT is going to be homeomorphic to two different knots in lens spaces. So each kind of Dane surgery that we would do to reveal a different filling to a knot complement also reveals a different name for QT, namely that it's a knot complement in one lens space and a knot complement in another lens space. And so for each one of those fillings, we have a knot that's embedded in these two lens spaces. And the conjecture is a little more amorphous, but it says that you can pick one of the two lens spaces here, and the knot, so let's just say LP P1 Q1 minus this K1 prime, that knot should be realized as either a 1-1 or a 1-2 knot in the lens space, or a 1-0 knot if we're just kind of putting the whole picture together. But in that case, QT would be ciphered fibered. So that doesn't fit into the hyperbolic side of the questions, but it does kind of neatly categorize the conjecture in terms of cyclic fillings, or manifolds QT with multiple cyclic fillings. Right, and in fact, there are examples of these knots and lens spaces with multiple lens space fillings where we can't see the Berge conjecture hold, that we do need these 1-2 knots. So in fact, and more than that, there are examples where the degree of this cover is 1, right? So these are they're asymmetric knots and lens spaces that have multiple cyclic fillings. So, these are, I guess what I'm saying is that these two conjectures, the Berge conjecture and then this conjecture of myself with Joan Licata and Ken Baker are different. They have a different flavor. Although, I guess relatedly, you could ask if you have a 1-2 knot in a lens space and it emits an S3 filling, is it necessarily does that necessarily mean that it's a Berge knot, so that you can also realize that 1-2 knot as a 1-1 knot somehow? So that gives you a way of kind of attacking and thinking about possible counterexamples for the Berge conjecture. Right. So I guess I was gonna shift over and talk about irregular quotients, but I figured I should maybe take a slight break to pause for questions here if anyone has them. Okay, so right. So that the picture that we've kind of just gone through and talked about what happens when we have a knot complement covering some orbifold in a regular way, and in that case, the cusp of the orbifold is going to be a torus or a sphere with 4 components of order 2, and in fact, we saw we can kind of knock things down to only have to worry about a knot complement covering an orbifold with a torus cusp, and really understand that problem to understand the full problem. Now, for irregular quotients, we have to worry about, to start out with, we have to worry about 3 types of cusp quotients. So those, and in fact, there are some knot complements that fit into this picture. What's being shown here are 20 crossing alternating knots, which are not the first things that people think about when they start drawing diagrams, right? But these specific knots are really pretty in the sense that, well, I guess the diagrams are pretty if you draw them in a pretty way. I'm not making any claims here, but these 2 knot complements actually decompose into 2 regular ideal dodecahedra. So these are knot complements of Ian Aitchison and Chaim Rubinstein. And they showed that, so they were able to build these knot complements that decompose into these 2 regular ideal dodecahedra. In fact, these are the only knot complements that decompose into any number of dodecahedra. And because of the underlying objects that they break up into, we can get a really small quotient. So these, using the symmetries of the regular ideal dodecahedron, we can get these things to irregularly cover some orbifold. So we can get both knot complements to irregularly cover, in fact, the same orbifold. And this leads to the following conjecture of Neumann and Reid, that the figure-8 knot complement and these 2 knot complements are the only knot complements which cover any orbifolds irregularly. So this is often said that they're the only knot complements with hidden symmetries. So one of the tricks and challenges is that there isn't a wealth of examples to really look at and probe when we're trying to understand this question. So of how we can see irregular quotients of knot complements, right? And also, I guess I should say that these 2 knot complements, they do cover an orbifold with an S2 333 cusp and an S2 236 cusp. So we see 2 out of the 3 cusp types showing up in the quotients of these 2 guys, and in fact, the same thing for the figure-8 knot complement. There's a quotient with only components of order 3 on its cusp, and there's a quotient with components of orders 2, 3, and 6. So we see 2 of the 3 cusp types, and that's not an accident. So it turns out that the 3rd cusp type just can't show up as in the quotient of a hyperbolic knot complement, which is really useful because a lot of times when we're trying to rule out hidden symmetries and these types of irregular quotients, there are really 3 flavors to those arguments where you're kind of just going cusp type by cusp type. So we can just cut out a third of our work in some sense. And we can even cut out 2/3 of our work by the next theorem. And that is that if you see if we saw S3 minus K covering some orbifold Q6 with a 2-3-6 cusp, then there has to be an intermediate cover with a 3-3-3 cusp, where the Q3 covers Q6, and it's a twofold cover. So really this theorem here comes from observing that if we have S3 minus K covering some orbifold with a 2-3-6 cusp, that this object has to have non-trivial abelianization, and that allows us to build that twofold cover. This is related, but not quite enough to settle a conjecture of Boileau, Boyer, Sabano, and Walsh. They conjectured that if you have a not admitting hidden symmetries, that you always see, whenever you see, say, an irregular cover, you always see a quotient down to an orbifold with a 2-3-6 case. You know, I can lazily say, like, maybe what you really wanted to say was that that you'd always have the S2 3-3-3 cusp, but you know, that's a complete sham of an argument. It's just by convenience in light of the other theorem, right? That, however, it is useful when you're investigating a commensurability class and trying to find maybe not complements that cover the minimal orbifold in the commensurability class, that you can lift to a twofold cover and know that any not complement would have to cover that intermediate object, just because, you know, you've made your computations a little more feasible by lifting up as, you know, as high as you can, right? So you're shrinking the size of this cover right here, right? So if you're trying to investigate, you know, what not complements might cover some orbifold, you can go a little bit higher. So it has a practical implication, but the actual question is really interesting. Like when you have, namely, like if you have an S3 minus K guy covering some orbifold with a 3-3-3 cusp, can we extend it? Like, is there naturally some extra bit of two torsion that's showing up on the cusp? And part of the challenge for all of these kinds of questions, as I said before, is that we don't have a wealth of examples. And in fact, even in terms of looking at good candidate orbifolds for Q6 or Q3, it's pretty challenging and difficult to find things that might fit into that picture, right? Like, so the examples from the previous slide, both the figure 8 not complement and these two not complements, they were kind of to the fact that both of them admit hidden symmetries is just kind of lucky in some sense, that we don't have an organic way of really producing objects along these lines. Right. Okay. So so this set of these two theorems together kind of actually say that, you know, we only need to look at a third of the cusps, right? So the problem got cut down to a third of its original size, in some sense. Right. So yeah. So along the, you know, in the spirit of trying to figure out how can we build not complements with hidden symmetries. So how can we find not complements that are regularly cover some object? We could ask, well, instead of the full Neumann and Reid conjecture that there are only just 3 of these things, we can ask for something slightly lighter, right? So this is an intermediate conjecture that that's joint work with, that came out of joint work with Eric Cheeseborough, Jason Du Bois, Christian Millichap, Preet Mundal, and Will Warden. And so what we said is, okay, well, if we fix a volume, how many knot complements emitting hidden symmetries could be below that certain volume? And our conjecture is that there should only be finitely many. And one of the things that we were able to establish is that if we look at a particularly, well, we can actually push that volume away from, 0 or the minimum volume for cusp hyperbolic 3 manifolds. We can push that to cover some non-trivial sets of manifolds. So in fact, if we have, in trying to understand what irregular covers look like, we're able to say that as long as if the volume is bigger than, or if the volume is less than 6 V naught, where V naught is the, let me go to black. Here, V naught is the volume of a regular ideal tetrahedron. So V naught is approximately 1.01 and change. So this is, if the hyperbolic volume is less than 6, for instance, then we know that the previous conjecture holds. And one thing that's very interesting about this is that there are lots of manifolds, and in fact, orbifolds that are covered by this theorem that also fit into the first part of the talk. So there are lots of ways of building commensurable knot complements that we know will not have hidden symmetries. So for instance, for the experts, the volume of the magic manifold, the so-called magic manifold, which just has all kinds of exceptional fillings, that has volume about 5.33. So that means that anytime we see some filling of the magic manifold that has more finite cyclic fillings, that the knot complements in those commensurability classes don't have hidden symmetries. So, that actually, and that allows us to really build more and more examples where we would have exactly 1 knot complement in the commensurability class, or exactly 2, or exactly 3, right? So that kind of gives a clean way of attacking that, or framing the conjecture, the original conjecture, and kind of producing infinite families of examples that fit into each one of the little boxes. Okay. So, and as part of this work, and really the ideas related to this conjecture, is that if the conjecture that below any fixed volume there are only finitely many knot complements emitting hidden symmetries, if that is false, then what we'd actually be able to produce is a link complement that covers an orbifold with a non-rigid cusp and a rigid cusp. So we'd have S3 minus Ki covering some Qi, and we might as well assume that these Qi's have a only three torsion on their cusp. And then we'd actually be able to build a geometric limit to S3 minus K, and these Qi's would limit to Q. And so we'd be able to understand this infinite family of covers in terms of covers of some link complement. And necessarily here, L is really, I'll put it in quotes a little bit, it would be K, it would have like a knotted component and then a bunch of other components. And this cusp K would cover, say, something rigid. You might as well assume that it's an S2333 cusp, and then all these other components would cover either S2222 cusps or T2 cusps. So my point is just that the cover here is a very specific object that we can get our hands on, and sort of looking at and restricting that cover allows us to actually build, or allows us to say that more and more knot complements don't have hidden symmetries. On top of that, the technology is advanced to actually be able to make effective statements along these lines. So we can rule out, we can say basically for the high parameter fillings, we just have to understand possible covers that are circled in blue, and for the low ones, we can check them by hand. So you can actually say that for certain link complements, you're never going to be able to produce knot complements that have hidden symmetries via surgery, right? So in that way, the conjecture is a useful tool for kind of probing questions along these lines. And so I also wanted to kind of mention what this kind of cover might look like, and just kind of give some examples of link complements that cover something with one of these kind of interesting cusps, and then some S222 or torus cusps. However, to really draw some nice pictures or talk about the intermediate covers really concretely, it helps to work with just 2 and 4 torsion. So this won't produce knot complements, but it should be in the right spirit of what we'd want to do with problems along these lines. And it gets to a really interesting phenomenon that shows up when studying problems like this. So this this link right here is the bromion rings, right? So the complement decomposes into 2 regular ideal octahedra, and it has this series of 2-fold quotients where we're quotienting out by symmetry, so let me just kind of color one of these cusps red here. So this first 2-fold symmetry, what happens is that it fixes points on the 2 blue cusps and acts freely on this red cusp. And so what that means is that the quotient, this initial 2-fold quotient, has a torus cusp, and then it has 2 quotients that are spheres with 4 cone points of order 2. And as we kind of go through and complete this picture, we can look at other 2-fold quotients so when we do that, what happens is that at this stage here, we actually introduce some 4 torsion. Sorry, we actually introduce some 4 torsion on the cusp. And sorry, I did one of these colorings wrong. So we introduce oh yeah, no, sorry. I should have done this one up here and this one up here. And so what we see is we've got these two, the two blue cusps, they cover the blue cusp down in the bottom, and allow us to do fillings on that blue cusp. Now, when you choose a one parameter family of fillings and lift it up, what happens is that if we're doing PQ filling on one of these, we're doing QP filling on the other. So that to respect the cover, you kind of have to do, to respect the cover, if you kind of choose a set of slopes that are going to lift, and kind of understand this cover in terms of lifting, there's a 2-to-1 map on that. Well, sorry, two cusps cover one cusp. So when we take one lift, that's going to prescribe what happens to the other one. But what it is saying is that the character variety of this object has some special properties, namely that we can find this parameterization on of this one parameter family of fillings on the two cusps that keep the cusp field here living in Q adjoin I. So you can, and then basically because everything's finite volume, there's only really finitely many choices for the cusp parameter here. So you can introduce an extra equation to the character variety and see that this is giving you a really interesting subvariety. So this is kind of in general, if you're able to fill cusps of a manifold and keep the cusp field kind of the same, or keep the cusp shape the same, you would call that geometric isolation. And this is really you might call this like parameterized isolation, geometric isolation. And so a natural question would be, can we see this parameterized geometric isolation in the cases of cusps that we care about in terms of hyperbolic knot complements, right? So the example that was just shown corresponds to the cusp that can't show up as a quotient of a hyperbolic knot complement. And then the other thing is, can we ever see parameterized isolation where we have this these cusps, like two cusps covering one cusp with a filling, where it's actually part of a more general phenomenon where we would see just general isolation. So it wouldn't matter which two cusps we could fill in the previous example. That doesn't happen here. That if you just take two arbitrary fillings of the bromine rings, the cusp field does not stay in Q adjoin I. In fact, will move around and not be in Q adjoin I. For instance, the double twist knots don't have cusp fields in Q adjoin I. So yeah, so I just wanted to say thanks. Yeah, and so I'll end with those two questions.
Well, first let's thank Neil. Any questions?
Sure. So, I mean, the classification of hyperbolic knots with hidden symmetries is really a conundrum, right? I mean, right now, where do you think the truth lies? Is it in the arithmetic? Is it in the geometry? Is it topological? What's going on here?
To be honest, I mean, one of the things that I guess I was that we've been thinking about along these lines is really trying to understand the orbifolds better. So these quotient orbifolds, to see what makes a good candidate for covers by a knot complement, because you have I think really part of the conundrum is that we don't understand, or we don't have a good set of quotient orbifolds to like look at and explore. Now, your question about I think your question might also be part of the frustration that it does have, there's a lot of different tools to understand and look at these problems, and it's unclear which set of tools could be helpful, or which one of these tools is going to have the most direct line. Mm-hmm. Yeah, I mean, the only thing I can say is that the algebraic side, like thinking about these objects in terms of finitely presented groups, can actually get us that seems to be actually where we've gotten the most mileage, in the sense that the theorems that I discussed here, where the cusp types were eliminated, it actually just came down to having the right generic presentations for these quotient orbifolds of knot complements, to where you could see basically actually both of these theorems are established by just finding the right twofold covers of something with a 244 cusp or something with a 236 cusp. And it's just writing down the peripheral subgroup and then the knot group in a nice way, and realizing that the meridians of the knot complement have to sit in a very prescribed way in terms of the quotient orbifold fundamental group. That namely the knot complement is the normal closure of a peripheral element is really kind of what allows you to attack these two theorems. So I mean, that's really just having a nice presentation in terms of the fundamental group, and that object also tends to be a pretty decent almost compression of a knot complement or an orbifold, right? So it's like got all of the information you need and maybe not any that you don't. Yeah, so that obviously that's not an answer to your question, but
it wasn't. It was more sort of philosophically what was going on. I mean, I find, somehow the hidden symmetry situation there, you're dealing with regular covers, and that is just much easier to understand. I'm quite baffled by irregular covers.
Yeah. Yeah, and so that's why we were trying to connect some of these questions to Dane surgery questions, right? Because like, your work really put the regular cover question, like you were able to kind of completely classify those questions or those issues in terms of Dane surgery, and just say, well, if we can connect it to well-known problems, right? And well-known constructions. So we were trying to, say, okay, well, that's maybe an advantage of the conjecture at the top of this page, is that it's not the full thing, right? But it's saying, like, if we're seeing a family where we can maybe get some geometric foothold, or we can attach it to objects that we know about, right? That we could at least eliminate a lot of cases. Really refine the problem to just checking some exceptional things that might happen.
there are no more questions, let's thank Neil again.